Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Alright, grade 11's new topic, quantitative aspects of chemical change, alright, or even some units call it qualitative aspects of chemical change, okay, which is probably more the right word, okay, but different textbooks use different, say quantitative or qualitative, okay, doesn't really matter. Basically we're dealing with aspects of chemical change. Okay, so once I finish taking off my warm jacket, because whenever I start talking I start getting warm, we will obviously start writing down some notes. Okay, so to begin, the first thing that we're going to approach, all right, is called the mole. Okay, we may or may not have heard about the mole before, maybe in talks, maybe from other students, previous years, maybe in the corridors of school, but the mole, we actually should have learnt in grade 10. Right? We should have touched on it in grade 10, okay? Which in grade 10 chemistry, where we learnt that the mole, what it is and what it's used for in stoichiometric calculations, okay? And in grade 11, we actually take this concept and we apply it to reactions that's involving gases and more complex stoichiometric calculations. In grade 10, they were very basic, very easy, and now in grade 11, we explore the mole in greater detail, okay? But to pull up its definition again of what it is, okay? It's, first of all, the mole is that quantity of matter containing, or that contains, exactly the same number, okay, that's where there's number of elementary particles as there are carbon 12, or let me say, instead of saying carbon 12 atoms, let's rather say carbon atoms in 12 grams of carbon, or of carbon 12. Okay, and the SI unit, okay, of the mole, whenever we use calculations, is we end off with whatever the value is, we end off with whatever the value is and the word mole for mole. Okay, cool. So that's basically a reminder of what the mole is. Okay, you know, carbon 12. If we look on our periodic table, if I could just get one open, the relative atomic mass of carbon is 12, all right, which is the carbon 12 atom, which is basically 12 grams per mole of carbon. Okay, so to read the definition again, the mole is a quantity of matter containing exactly the same number of elementary particles as there are carbon 12 atoms in carbon atoms in 12 grams of carbon 12. Okay, and that's basically a recap of what the mole is, and we take this a little bit further in grade 11. Okay, and we're going to touch base again on some of the of those terms, and we're also going to introduce something called Avogadro's number. Okay, now Avogadro, okay, which I will speak about in just a moment. Okay, it's a specific number that's given as a constant in our exam, right, in our table of constants. Okay, basically what we are saying is that 1 mole of a substance contains a fixed amount or fixed number of particles, and that is known as Avogadro's number, okay, which has a value. Some textbooks give it to 2 or 3 decimal places depending on the textbook. However, I'm using the one that I have here, which is 6,02 times 10 to the power of 23. So let's just get that definition down, and then I will display an example. So basically they're saying that Avogadro's number is saying that 1 mole of any substance, right? 1 mole of a substance contains a fixed number of particles, and that's known as Avogadro's number. Did I spell it correctly? Just check. Avogadro's number. I'm going to use NO for now. Okay. And that value, of course, is equal, just at the bottom here, to 6,02 times 10 to the power of 23. Okay. So, for example, at the bottom here, 1 mole of H2O, alright, 1 mole of H2O basically is 6,02 times 10 to the power of 23 H2O molecules in 1 mole of water. Okay, so 1 mole of H2O, 1 mole of water is saying that there's 6,02 times 10 to the power of 23 water molecules in 1 mole of water. Okay, and there's a formula that we can use for this, which I will display on the next slide. And that formula for Avogadro's number, okay, Avogadro's number formula is N is equal to N, capital N, divided by NA. Okay, so N is basically the number of particles, so NO stands for number of particles. Let's do little n. Little n over there is basically the number of moles, and then Na, you guessed it, this is Avogadro's number. Okay, in the formula. Okay, so if you're trying to find out the number of moles of a substance, but you know the number of particles, take it divided by Avogadro's number, it'll give you the number of moles, and so on and so forth. If you have the number of moles as well as Avogadro's number, you can find the number of particles within any molecule. Alright, so that's how that formula works, kind of basic. Okay, then again from last year as well, we should have known this formula, but we should have also discussed molar mass. In fact, I'll use another color for it. Let's use the one next to it. Molar mass. Okay. So, molar mass, okay, which is the mass of 1 mole of a substance, okay, and its unit is grams per mole to the -1, okay. So the mass of 1 mole of a substance is the relative formula mass of that substance expressed in grams, okay. Now, the molar mass is basically the mass per mole, okay, the mass per mole of a substance, okay, and it's used as big M, okay. Where we define, therefore, the formula of a mole is the number of moles is equal to the mass of that particular substance, all divided by the molar mass of that particular substance, okay. And we know this is in mole, and this is grams per mole, okay, grams and in grams per mole, and that is in mole, okay, fantastic. Okay, so that's all I think that we know about qualitative aspects of chemical change so far, okay, and this is a little bit of a summary, okay, but first we've got to go and discuss a little bit more about molar volume of gases, okay, which I don't believe was discussed last year in grade 10, but it's called molar volume of gases, okay. So if we go over here, and I'll use another color, molar volume of gases. In gas laws, there is a a guy by the name of Gay-Lussac, okay, or in the 19th century, all right, and he discovered that volumes of all reacting gases and the volumes of the gaseous products of these reactions are in simple ratios. Okay, they're in ratios of whole numbers, providing that volumes are measured under the same conditions. So this is how we get mole ratios. Okay, so in other words, 2 volumes of H2 gas plus 1 volume or 1 molar volume of O2 gas basically gives us 2 volumes of H2O gas. Okay, and this obviously is taken from where? We all should remember this. We've got hydrogen plus oxygen. We know we end up with H2O, but it's an unbalanced equation, is it not? So if we balance up our oxygens over here, and we have to balance up our hydrogens over here, so we end up with this. So here, just to put a dotted one there, we end up with the same thing. 2 volumes of hydrogen reacting with 1 volume of oxygen gives us 2 volumes of hydrogen. Okay, the mole ratio is taken from the balancing numbers. So we never balanced anything, all right, for no reason. Okay, and the same thing can be applied with nitrogen and hydrogen forming ammonia. All right, simple balancing of equations. Okay, then basically Avogadro, who was Italian, all right, he came along and then he basically expanded on this. Okay, and he expanded on this by stating that equal volumes of gases contain equal number of particles, obviously provided that temperature and pressure are still the same. Okay, so we came along and basically determined that 1 mole of a gas, okay, 1 mole of a gas basically occupies, right, 22.4 decimeters cube, all right, at standard temperature. Now standard temperature, if anybody doesn't know what standard temperature is, I'm going to tell you, standard temperature is 0 degrees Celsius. Okay? And standard pressure is basically 1 kilopascal. Oh, not 1 kilopascal, sorry, 101 kilopascals. Okay? Which basically saying 101.3 kilopascals, which is 1 atmosphere. 1 atmosphere is 101.3 kilopascals. Okay, so what does this mean? Both together, standard temperature and standard pressure basically form something that is called STP. So if you get a question, what is the molar volume at STP? They're asking what is the molar volume at standard temperature, pressure, or standard temperature, standard pressure. Okay. So to explain that theory, basically he discovered that since a mole contains the fixed number of particles, it follows that 1 mole of any gas must occupy that same volume under the same temperature and pressure conditions, which is now known as molar volume of a particular gas. Therefore, the formula is as follows. N is equal to V over Vm. Okay? V stands for volume. Alright? And your volume, okay, is equal to whatever it is in decimeters cubed. Okay? Your Vm is your molar volume. Molar volume, which is decimeters cubed per mole. Alright? Decimeters cubed per mole. Alright? So, what is your molar volume all the time? 22.4 decimeters cubed is your molar volume. Okay, and N is the number of moles. Okay, so in summary, we've got 3 formula for the mole. 1 mole contains 6.02 times 10 to the power of 23 particles, which is Avogadro's number. N is equal to N over Na. 1 mole also has a mass equal to the molar mass in grams, alright, or the relative atomic mass in grams. So that is your normal mole calculation that we learned in grade 10. N is equal to mass of the substance divided by the molar mass of the substance. And then, of course, 1 mole of gas at STP has a volume of 22,4 decimeters cubed, which is this formula that we see over here. So there are 3 formulas now, or formulae now, that exist to calculate the mole, not just N is equal to M over big M. Now that's a lot of stuff we've just explained. Let's take a little bit of an example, and let's see how we can work it out. And let's have a look at applications of reactions that also produce gases, and then we'll be practicing a few questions. Okay, let me just check, where are we now? Okay, cool. And then we move on to concentration. Okay, so where's my mouse? There we go. Oh, pardon me. Are there any questions so far? Okay, so guys, the exercise that I sent through on the WhatsApp group was exercise 3.1. Okay, and this is from the textbook. The textbook that I'm using here is just physical. It's just called Physical Sciences, grade 11. Grade 11, and the it's just theory exercises and practical investigation, and it's by a guy called J.M. Lucas. Okay, J.M. Lucas. Okay, that's the textbook that I'm using. Very good textbook. Yeah, I think it's called The Science Tutor. That's what it says on the cover. The Science Tutor. Anyway, question 1.1 says calculate the number of moles in the following. So they gave us 30 decimeters cube of oxygen gas, so of O2 gas, and of course that was at STP, and they want the number of moles. So of course, number of moles, they gave us volume, so V over Vm, which is equal to 30 divided by 22,4. And let's see, therefore, the number of moles is equal to, anybody have an answer?
1,34 decimeters cubed.
Okay, cool. 1,34 is the correct number. Alex, just watch that. We're calculating number of moles. So it's 1,34 mole. 1,34 mole. Okay, good job though. Got the number correctly. You knew what to do. You plugged it in correctly. So good job on that. We're making some good progress there. Excellent. 1.2. This was now 10 decimeters cubed of helium gas, right? Also at STP. Standard temperature pressure. Same formula. N is equal to V divided by Vm, which is equal to 10 divided by 22,4. Anybody have an answer here? Divided by 32,4. Answer, please.
I got 0,45 mole.
Very good. Very good, Kelly, as well. 0,45 mole. Excellent. Ow, sorry. Excellent. So that was excellent answer there. Well done. Excellent little warm-up questions. We're doing well so far. Okay. Let's get that answer there. 1,34 mole for the first one of oxygen gas, 30 decimeter cubed. For the 10 decimeters of helium at STP, 0,45 mole. Okay, switch up the color a little bit. Question 2. They say sulfur burns in excess and forms sulfur dioxide. If 16 grams of sulfur are burnt, what volume of SO2 is formed at STP? Okay, so first things here is we take our mole formula, M divided by big M, because we need the number of moles first. Okay, so here we go and we say, well, that's 16 grams divided by SO2, well, I think the molar mass there is, well, 32 plus 16 times 2, so 32 plus 32, so I think it's 64. It's the molar mass there. And if we check that on our calculator, 16 divided by 64, we end up with 0.25. Alright, therefore, number of moles is 0.25 mole. And now they want to know the volume of SO2 formed. So N is equal to V divided by Vm, which is equal to 0.25 is equal to V divided by 22,4. We take our answer, we times it by 22,4. Let's just see. Okay, something that I've missed out on. Yes, I've missed out on something. Sorry, let me just reapproach this question quickly. Probably is best to write out a reaction quickly. Sorry, I missed it. I missed something very important. 16 grams was not SO2, so we had sulfur, which was S plus O2 plus O2, and that gave us SO2. Okay, and they say, well, 16 grams of sulfur was burnt, so we need to check, okay, what's the number of moles of sulfur? M divided by big M, so that's 16 divided by 32, right? And that should give us, just check if my math is correct, divided by 32, should give us a half, 0.5 mole. So 0.5 mole of sulfur is for the 16 grams of sulfur that burnt. Okay, and now they want to know if 16 grams of sulfur burnt, okay, then what is the number of moles, or volume rather, of SO2 that was formed. So because they are in the same mole ratio, okay, they are perfectly balanced, of course. So now we know that N is equal to V divided by Vm. Now this is right, so we sub in 0.5 now, and that's equal to V divided by 22,4 times both sides by 22,4, and therefore the volume of SO2 that was formed at STP is now equal to, it should be 11,2, yes. 11,2 decimeters cubed. Okay, I did that question because I cocked up the reading. Sorry, I messed that one up, guys. But yeah, that's the final answer. So, who got 11,2 decimeters cubed for question 2? Anybody? Anybody get 11,2? I'd like to know. If you didn't, it's okay. You can let me know you didn't. Okay, Connor got it. Excellent. Fantastic. Okay, cool. We won't ponder on this one too much. Cool. Let's go to number 3. Okay. Number 3 said when potassium chlorate is heated, it decomposes to form the potassium chloride and oxygen, and it was given by the equation KClO3. Potassium chlorate gave us KCl plus oxygen, gas, and this is unbalanced. Okay, so they ask us now what volume of oxygen at STP will be produced when 24,5 grams of potassium chlorate is or are decomposed. First thing we need to do is we need to balance the equation. Okay, so I'm going to double this one up, my oxygens, then I need to double everything up here, and then I probably need to triple everything up here. So 2 KCl, 2 KCl, but now I've got 6 oxygens and 6 oxygens. Now everything is balanced on my side. Okay, so they told us that they want to know what volume of oxygen. So V of O2 is what we want to know. but they gave us the mass of potassium chlorate to be 24,5 grams, and the molar mass of KClO3 as about 122,5 grams per mole. Okay, because that's just from the periodic table. Okay, so let's find out the volume of oxygen. So first thing you do, we work with this one first. Okay, so we say N is equal to M divided by big M. We know that's 24,5 divided by 122,5. And therefore, number of moles of potassium chlorate is equal to 0,2 mole. Okay, now that we have that, we need to put it in the mole ratio of 2:3. Okay, we have a 2:3 ratio here. So we have 0,2, and this is x, in other words, it's unknown. So I need to divide it by 2, multiply it by 3. Okay, because this is over 3. So divide by 2, multiply by 3 to get x. Okay, we'll take 3 here, that disappears, and 3 times this whole thing. Okay, so let's do that. So 0,2 divided by 2 times by 3, basically x is equal to 0,3 mole. Okay, and x was the oxygen gas. Okay, so 0,3. Now that we know the amount of moles of oxygen that was formed according to the reaction, therefore N should be equal to V divided by Vm. No idea why I wrote this so big, but anyway, let's just keep going with it. And can't put the equals there. So now we've got 0,3 is equal to V divided by 22,4. 0,3 times 22,4 gives us an answer. Let's make sure I'm correct. I might be wrong. Yeah, there we go. I am correct according to my calculations. Therefore, the volume of oxygen gas that was formed when 24,5 grams of calcium chlorate decomposed was 6,72 decimeters cube. Okay, anybody get that? Right, question 4. Now they had a little bit of a graph, and it shows the volume of chlorine gas produced at STP, and they gave us a reaction. So they gave us 4HCl plus MnO2, gave us chlorine gas plus MnCl2 plus 2H2O. Okay, perfectly balanced equation. 4.1 now says calculate the mass of HCl that reacted. Okay, all the info that we've been given is that the volume of Cl2 produced at STP was 10 decimeters cubed. So the first thing that we do first is we take, well, the number of moles of Cl2 that produced for 10 decimeters cubed is equal to the following. 10 divided by 22,4. Therefore, the number of moles of chlorine gas that produced was 10 divided by 22,4, and that is 0,4464. So let's make it 0,446 mole. So now what have we got here, boys and girls? We got the number of moles for this volume of Cl2. Okay? That's all. That's what we needed. Okay? Now we use the mole ratio. Okay? We got a 4:1 mole ratio, and we basically, this is what we need to find out, number of moles of HCl that reacted, so this could form. So 0,446 moles of Cl2 gas could form. Okay, so basically all we're going to do is divide by 1 and times by 4, and therefore x is going to equal 0,446 times by 4, because divide by 1 is itself anyway, is 1,784 mole. Okay, and which is basically the number of moles of HCl. Okay, now that we've got that, very easy now, we can just say the number of moles of HCl. Maybe I'll switch back here to this color because I'm going down to the bottom. Number of moles of HCl is equal to the mass divided by the molar mass. Now we found out the number of moles. It is 1,784 is equal to the mass in grams, which is unknown, but the molar mass we can still find out. That's about 30. No, am I right? No, that is 36,5 for the whole thing, because hydrogen is just 1. So 36,5. And we'll take that answer 1,784 times by 36,5, and we'll end up with the mass of HCl, alright, that reacted with however much of MnO2 is equal to 65,116, so basically 65,1, make it 65,12 grams of HCl that reacted. 4.2's question was how many chlorine molecules were produced in the reaction? Well, now we're asking for Avogadro's number. So now back to the formula, N is equal to capital N, which is the number of particles, and divided by, or number of molecules divided by Avogadro's number. So we know the number of moles of chlorine gas that was produced. It was 0,446. We calculated that. So 0,446 is equal to N divided by 6,02 times 10 to the power of 23. Alright, that's how it works. Okay, so we're just going to multiply normal equation, multiply both sides by Avogadro's number. There, 4, 0,446 times bracket 6,02 times 10 to the power of 23. Let's just check what we have here. That's about 2,68492 times 10 to the power of 23. So we can round that up to about 2,7 or 2,68 if you wish. I'm going to round the 6 up to 7 times 10 to the power of 23, and we can end it off nicely. Cl2 molecules. Alright, Cl2 molecules. There we go. And that's it. So that's the number of molecules that were present in 0,446 moles of Cl2 gas. Okay. Easy, quite simple. Alright, if you just follow the steps. Okay, not that difficult. Let me rather say that. It's not that difficult. I think we have time for one more. This is only 22 minutes past 5. So we have time for one more. And let's give question 5 a crack. Alright guys, it's about 5:26, so I know we've got about like 4 minutes. So I just want to get question 5 in quickly. And then we can have a look at the rest of that activity for extra practice. Okay, so question 5 says carbon reacts with hydrogen to form methane. Okay, in the reaction that's given here, plus H2 gas, and there's a balancing 2 in front here that gives us CH4 gas. And 5.1 now says how many grams of carbon are required to form 44.8 decimeters cubed of methane gas at STP. Very good question. So we are given the volume of methane gas. So we need to find out, okay, what is the mole of that volume? Okay. So we know that is 44.8 divided by 22.4. Basically, the number of moles of methane gas is 2 moles. So for this volume, 2 moles of STP. Okay. Now because the question says how many grams of carbon are required to form this amount of volume of methane, they are in the same mole ratio of 1:1. So 2 moles of methane is 2 moles of carbon as well. They are the same. Okay, so they are both 2. So therefore we come to our other formula. N is equal to M divided by capital M. Alright, moles of carbon are 2. Mass, we're trying to find out how many grams, and we know that the molar mass of carbon is 12. Times both sides by 12. Therefore, the mass of carbon that is needed or required to form 44.8 decimeters cubed of methane gas is 24 grams. Right? All we did was work backwards and with the mole ratio. And this was 5.1. Just going to rule a line down the middle here. And just change the color slightly. 5.2 asked us the question, if 11.2 decimeters cubed of hydrogen gas were used or are used, what volume of methane gas is therefore formed? So we do the same thing. Number of mole of H2 gas is equal to V divided by Vm. So 11.2 is given, divided by 22.4, basically gives us 0.5 mole. Same mole ratio, sorry, not the same mole ratio, but they are in the mole ratio of 2:1. So if this one is 0.5 divided by 2 times 1 is 0.25 mole. So 0.25 moles basically produces of H2 gas produces 0.25 moles of methane. And again, they asked if that was the volume of hydrogen gas, what volume of methane would be formed? Okay, so therefore N is equal to V divided by Vm. Number of moles of methane now is 0.25. Is equal to the volume divided by 22.4, and therefore we times both sides by 22.4, and therefore the volume of methane formed if 11.2 decimeters cubed of hydrogen gas were used is now 5.6 decimeters cubed. And that brings us to the actual end of our session and the end of question 5. And that brings us also to the end of our presentation, grade 11s. Thank you so much. When we come back next week, we will look at concentration as the follow-on topic from molar volume.